Hello and welcome to the YouTube channel for Boone English School. In this series of videos, what I intend to do is to provide you with necessary and sufficient material for ICSE 2026. The subject that I will be dealing with is physics. My name is Yash Singh Jha and I teach physics at Boone English School. The first chapter that we will deal with is force. Let's get on with it. Giving you a brief overview of what we are going to look at is what force is, what are the effects of force, translational and rotational motion, turning force, moment of a force, center of gravity, and uniform circular motion. So, what is force? The purpose of this lecture is also to induce in you a genuine curiosity for the subject. Physics, by definition, is the study of the universe around you. So, everything and whatever that happens around you can be studied, and that study is called physics. Yes? We want to know the cause behind why things happen. And one of those causes is force. Yeah, so if you can see here, the force is that physical cause. It's a cause. Force causes things to happen. Yes, what happens? It changes or tends to change. It changes or tends to change what? The state of rest or the state of uniform motion of a body in a straight line. Yes, in earlier classes you must have gone through certain definition of force, like a push or a pull is called a force. Yes, this is just a much more refined version of what force is. Yes, first of all, one thing that we should notice is the word cause. Force is a physical cause that changes or tends to change. Why tends to change? Sometimes the force may not be big enough to cause a change. For example, a baby pushing a car. Yes, the baby is applying a force, yet that force is not strong enough to overpower the inertia of the car. Right? So a force either changes or tends to change. What does it change? The state of rest or the state of uniform motion of a body in a straight line. Yeah, if it's not clear, it will be clear in the following slides. Yes, moving on. The cause has some effects. Yeah, the cause is always followed by an effect. The effect can be either pushing, pulling, stretching, squeezing, compressing, and so on. Yeah, so few of the examples are, if the force causes a pushing action, pushing effect, the examples are pushing a chair, pushing a car, flapping of wings by birds, etc. Yeah, force as a pull, pulling a door, train pulling a carriage, yeah, the thela wala, the cart guy. Or you can stretching of rubber band, stretching of a string of bow, stretching of a spring. Force as a squeeze, yeah, squeezing wet clothes, yeah, toothpaste tube, chewing gum. Compress, force as a compress, when you compress the cotton, or the hydraulic presses that compresses, yeah, seeds and gets oil out of it, yeah, or the compressed natural gas. Yeah. Moving on and looking into each of them in a greater detail, force as a push, yeah, it is the lecture is designed in such a way as to appeal to your common sense. Yeah, there is not much intellect required. Yeah, which invites intuition to come into action. Yeah, so let's move on. What is force as a push? A body is said to be pushed if direction of motion is away from the source of force applied. Yeah, there is a car and the man is applying a force. Yeah, the car will move in this direction and the force is also being applied in the same direction. Yes, so direction of motion is away from the source of force applied. We are just giving words to commonsensical things. Yes, this is an example of force as a push. Second, when the birds flap its wings up and down, what happens? The wings push the air below it. The wings push the air below it, and as a result, the bird flies. Yeah, moving on, force as a pull. A body is said to be pulled if the direction of motion is towards the source of force. Again, a very commonsensical thing. Here you can see a man pulling a cart. So the man is applying a force towards himself. Yes? So the direction of motion is towards the source of force applied. Second example can be train pulling the bogies. That the engine, the powerhouse of the train, it applies a force or pulls the force in the direction of motion. Yeah? And as a result, the bogies move towards the source of force. Moving on, force as a stretch. Yes, a body is said to be stretched. Why and when? If a force applied on it stretches its length and direction of its motion along the direction of force. Yes, what does it mean? If there is an unstretched string, you place a bob and let it extend. What happens? The length of the string increases. Yes, and the direction of motion is along the direction of force. Yeah, the weight acts downwards and the direction of motion is along the direction of force. That is when we say that the force has caused a stretch. Yeah, other example is when a bow is used, right? So in normal condition, when it's not stretched, the string will be straight. Yes, but when we apply a force and stretch the string in this direction, the string becomes stretched. Yeah, the length of the string has increased and direction of motion is along the direction of force. Force can also be or can also cause squeezing. Yeah? A body is said to be squeezed if a force applied on it changes its shape. The examples are something that we do daily. What is that? Squeezing a toothpaste to get the paste out. Yes, or before drying the clothes, what do? We squeeze the clothes to get the water out. Yeah, these are the examples of force as a squeeze. You can also compress using a force. A force can also compress something. Where have we seen it? Yeah, we have seen it in compressed gas. Yeah, there is a tank, and in the tank there is a gas. There are gas particles, and using a piston we compress it, reducing the volume of the piston of the gas. So what happens when we compress? The volume decreases or the dimensions decrease. Yes, or when we compress a cotton or a sponge. Yes, when we compress a sponge, what happens? The dimension or the volume of the sponge decreases. That is when we say that the force has compressed a sponge, has compressed a cotton. There are a few important things to understand. First, the force can change the state of rest or motion. Motion includes two things. Number one, speed or direction. Yeah. In addition to that, it may also change the shape and size. Yeah. Or it can cause all of this together. Yes. How can it change the state of rest? There is a block of mass kept on the ground, and if you apply some force on it, F, it starts moving in the direction. Yes. How does it change the motion? By accelerating a car, we can increase the speed of the car, or by applying a brake on it, the braking force, the speed can decrease. So the speed of motion can change by a force. Direction, how can we change the direction? We see it all the time on a football ground. Yeah, a football is moving in a certain direction, and when a certain player kicks it in a different direction, the ball changes in this direction. Yes, or in billiards or wherever. badminton, etc. What else? It can change the shape and size. We saw that, right? When we compress a sponge, the size and shape of the sponge changes. Either these can happen individually or all can happen together. That is what force does. Next, force always exists in pairs and in opposite directions to each other. It's a consequence of Newton's third law of motion. Yes, every action has an equal and opposite reaction to it. Yes, so forces always exist in pairs and in opposite direction. What is the example? Example is, there is a table, and on the table there is a book. Book is kept on top of a table. Now what happens? The book has a weight. The weight is downwards, vertically downwards, right? And the table applies a force, normal reaction force. Yes? And the book isn't moving anywhere, so normal equals mg. So the weight of the book generated a normal reaction force which is equal to the weight but in opposite direction, which enables the book to stay still on the table. Yes? What next? The change takes place in direction of resultant force. The example is tug of war. Yeah? So there is a tug of war happening between two persons, two people, and the block will move in the direction of the stronger person, of the greater force. Yes? So if there is a force F3 in left and F4 towards the right, the resultant force will be something F4 minus F3 towards the right. Yes? And the block will move in the direction of the resultant force. Yeah? Second, what next? The greater the force, the greater the change. What does it mean? The change or the proportion of change depends on the force. How? First, there is an unstretched spring. On placing a mass M having a weight W, it stretched, let's say, L. If we place a greater mass, then the stretching will be more. Yes, greater the weight that the spring holds, greater would be the extension. Greater would be the stretch. Yeah. On releasing the external force, the object tends to acquire its original shape. Yeah. If I remove this mass, what happens? The spring will go back to its original position, original configuration. Moving on, the effects of a force. Yes, that is what we wanted to know since the very beginning. Yeah, how do things happen? Yes, force is a cause. So what are the effects? We have already looked at it. Let us revise. First, we can categorize it into three classes. What's the first one? Change the dimension of a non-rigid body. Yeah, change the dimension of a non-rigid body. Second, force can make an object move or can stop a moving object. Yes, force can change the speed or direction of motion or both. Yeah, let's look into each of it in a greater detail. First is, the force can change the dimension of a non-rigid body. What do you mean by a rigid and a non-rigid body? Yeah, so a rigid body is one whose particles are so strongly bound that any force cannot cause a change in its dimensions. Yeah, basically a rigid body is a body in which any force cannot cause a change in its shape, change in its dimensions. Yeah? A non-rigid body, on the other hand, is the opposite of a rigid body. What do I mean by that? A non-rigid body is the one in which force can cause a change in its dimensions. Yes? Simple. Moving on, what I am trying to say here is the force can change the dimension of a non-rigid body. Yes, and when the force is removed, the object does not restore back into its original position, as there is virtually no restoring force within the body. Yes, What are the examples of this line? The examples are when we make a roti at house, chapati at house. Yeah, the wheat dough that we make, it is circular in shape, and then we compress it and make it circular into a chapati. Yes, so the shape of the non-rigid body has changed. Yeah, and by removing the force, the shape hasn't gone back to its original shape. Yes, other example is a mud. The mud or the clay, we can make it into such a beautiful idols. Yes, but by removing the force or the hand of the artist, the idol doesn't become mud again. Why is that? It's because the restoring force within the body is not enough to go back to the original position. Yes, so the force can change the dimension of a non-rigid body. Second, force can make an object move or can stop a moving object. Yeah, we have discussed it already. Let me go over it again. When the force is applied on a rigid body at rest, it starts moving in direction of the force. Example is a football kick. When the kick is done, the ball moves from a state of rest to motion. Yes, also when the force is applied in the direction of opposite to that of the motion, the body can be stopped. Example is again in a football, when the goalkeeper holds or grabs onto the moving ball to stop a goal. Yes, so the ball was moving, on application of force, the football stopped. Yes, moving ahead. The force can change the speed or the direction of motion or both. Yes, when force is applied on a moving body in the direction of motion, it starts moving faster. Example is an accelerating car. Yes. Second, when force is applied on a moving body in direction opposite to that of motion, what happens? It starts slowing down. Yeah. The example can be when you apply brakes on a moving car. Yes. If the direction of force makes any angle other than 0 degrees and 180 degrees, it changes the speed or direction of motion or both. Yes, what are the special cases? Special case is when the force and direction of motion makes 90 degrees to each other, like for example in a circular motion. Yeah, the force, which is called a centripetal force, which we are going to study later, is acting towards the center. Yeah, and direction of motion is always tangent to the circle. So the force is always perpendicular to direction of motion, that is it makes 90 degrees to direction of motion. Yeah, in case of a uniform circular motion, only the direction of motion is changing at every point of the circle, but the speed remains the same. Yes, the other example can be when an apple falls from a tree. Yeah, speed of the apple keeps on increasing with time until it hits the ground. Yeah, the taller the tree, the greater the speed with which the apple hits the ground. Yeah, so this is the reason why in apple orchards, when the height of the tree is very big, they place something to hold the apple so that the apple doesn't damage itself by falling. So what does a force do? It can either make an object move or can stop a moving object. It can change dimension of some non-rigid body, or it can change the speed or direction of motion or both. Yes, there are certain important things to understand. First, force is not needed to keep a body in motion. Why is this important to understand? Because it is something that practically we cannot relate. Yes, whenever we put a force, the body moves. When the force is removed, the body stops. This is what our experience is. When we play football, when I kick, the ball doesn't go on forever. Yes, it stops. Why does it stop? Because there are opposing forces. There is air drag, there is friction from the ground which stops the ball. Yes, in an ideal world, when there is no friction, no air resistance, if I kick a football, the football will go on forever. Yes. Second point to notice, an isolated body requires no force to keep moving with constant velocity. Yes, the 2 points are the same but in different words. That means if the football is already moving with a constant velocity and any other external force is not acting on the football, what will happen? It will keep on moving with the constant velocity. Yes. Next, Newton's second law of motion. I am sure you must have learnt it in previous classes. Yeah, the force on a body is mass multiplied by the acceleration produced. Yeah. So this is the first instance of a cause effect equation. Yeah. What does it mean? F is a force which when applied on a mass m causes an acceleration a. Yeah, I'm going to repeat it again. So there is a mass m on which a force F is applied. Yeah, what happens? The consequence is that the mass m starts moving with an acceleration a. With an acceleration a. Yes, so force F is a force which when acted on a mass m produces an acceleration a. That is the consequence of the cause effect relation F equals ma. Yes. So in CGS system, the unit of force is dyne. Why do we need units? To be able to talk to other people, to be able to communicate. Yes, you go to a shop and you say I need 5 liters of oil. You don't say I need 5 kgs or 5 bananas of oil, right? That is why units are required. So when we want to explain the universe around us, we need a way of measuring things, measuring forces. Yes, so in CGS system, the unit of force is dyne. 1 dyne is a force that acts on a body of mass m, 1 gram, and produces an acceleration a, 1 centimeter per second square. Yes, so let me write it down again. 1 dyne is a force which when acted on a mass of 1 grams produces an acceleration of 1 centimeter per second square. Yes, 1 dyne is the force which when acted on a mass of 1 gram produces an acceleration of 1 centimeter per second square. Similarly, in SI system, we have the unit of force to be Newton. So, is defined in a similar way. 1 Newton is the force which when acted on a mass 1 kilograms produces an acceleration of 1 meter per second square. Yes, the definition of 1 Newton and 1 dyne follows the definition that we had for F equals ma. Yes, so what is the relation between Newton and dyne? It is as follows. 1 Newton is 1 kg times 1 meter per second square. 1 kg is again in turn 10 to the power 3 grams, that is 1000 grams. 1 meter per second square is again 100 centimeter per second square or 10 to the power 2 centimeter per second square, which gives us 10 to the power 5 gram centimeter per second square or 10 to the power 5 dyne. Yes, so 1 Newton is 10 to the power 5 dyne. So, from the previous definition of force, as per Newton's second law, that is the F equals ma relation, the cause effect relation. Yeah? So, force as a cause causes what? Causes masses to accelerate. That is, loosely we can say that force is what causes motion to happen. Yes, and the motion can also be categorized into 2 classes. The first is a translational motion and second is a rotational motion. Yeah, and as the name suggests, if the force is applied on a rigid body and the body rotates about a certain axis, such motion is called rotational motion. And if a body is applied on a rigid body and the body moves in a straight line or along a path, such motion is called translational motion. The examples are a windmill. Like in a windmill, the blades of a windmill rotate about the center. So the windmill blades are rotating, and it's an example of rotational motion. Yes. The race car, travels in a straight line or along a path. Hence, the car is translating. Yeah, car is moving. Yes. At the same time, if you look at the wheels of the car, what happens? The wheels are continuously rotating about its own axis. Yes. So this indeed tells us that it is possible for one object to be doing both together, to be both translating and rotating. Yes, the example is a race car. The car itself is translating, yet the wheels of the race car are also rotating about their own axis. Yes, so force causes motion to happen, and the motion can be categorized into translational and rotational. As the name suggests, if the body rotates, it is rotational motion. If the body moves in a straight line or along a path, that motion is called translational motion. Moving ahead, one of the effects of force, as we saw earlier, there are many, right? There were pushing, pulling, compressing, stretching. Yeah, so one of them is turning. Yes, turning things, rotating things. Yes, so again you are going to express something in words, something which is very commonsensical, which is if a force is applied and the body rotates about a fixed point, that force is called turning force. Yes, if a force is applied and the body rotates about a fixed point, that force is called a turning force. For example, if there is a door, this is a door, and this is the hinge. These are the hinge. What do? We apply a force, and the force turns the door open. Yes, so the force turns the door open. Yes, so when a force is applied at a point of the fixed body, we apply the force on the handle. The body rotates about the fixed axis. Here the axis is the hinge, the wall. Yeah, so that force is called a turning force. There are other examples, like when you open a tap, what happens? You apply forces with your fingers here and here, due to which the tap turns open. Yes. The other example is using a spanner. In a spanner, what happens? You apply a force in this direction here and in the lower end in that direction. These two forces together produce a turning effect in this direction and the nut opens. Those are the examples of turning force, something that we have seen in our daily lives. Okay, the forces can cause turning to happen, but we have noticed that turning depends upon force and one other factor. For example, in the previous slide, we looked at a door, right? We have a handle which is away from the hinge. If we had a handle which is very close to the hinge, opening a door would be difficult. Yes, if this doesn't appeal to you, you may just go to your homes wherever there is a door and just try it for yourself. Yes, applying a force away from the hinge makes our job considerably easier. So the same force is producing different turning effects, different quantities of turning effects. Yes, so there must be some way of quantifying the turning effect of a force. Yeah, and that quantity is called torque. What is torque? Torque is the quantification of the turning effect of force. Yes, how much turning effect is produced by this force when applied at such point. Yeah, so the turning effect of a force acting on a body about an axis is called moment of a force or torque. Yeah, so whatever I explained to you, it's the same thing written in a different way. Yes, the turning effect of a force acting on the body about an axis is called moment of a force. So there are two factors that we discussed, right? First, the magnitude of force. How much force are you applying? Yes. Second is the distance of line of action of force from the axis of rotation. What do you mean by line of action? Yeah. Suppose there is an object like this, which is hinged at point O, and we have a force acting on the body in this direction at this point. Yeah? So line of action is an imaginary line in the direction of force. So this line, which is imaginary is called line of action. What is line of action? It's an imaginary line in the direction of force. Yes. The distance of line of action of force from the axis of rotation. So this is the axis of rotation. From here, this distance is what determines the magnitude of torque. Let's say this distance is F, D, and this force is F. So the torque produced is F times D. Suppose there was another force. The force was acting in this direction. This is the force acting. The line of action in this case would be this dotted line. Yeah, and the distance between the axis and the line of action would be this distance, the perpendicular, the shortest distance. Let this distance be d2 and this force be F2. So torque in this case, second case, would be F2 times d2. A very simple calculation. Yeah. In the case of the spanner, you can see here force is applied at the end and the length of the spanner is L. So the quantity of torque produced is force applied F times the distance between the line of action and the axis of rotation. This is the distance. So F into L. Yeah, this is the reason why we have long spanners. Yeah, why the handles of spanners is made long. Yeah, to reduce the effort, to maximize the amount of torque produced. Yes, larger or longer the spanner, the greater is the torque produced. Yes, moving on. What do I mean by direction of turning or rotation? On applying the force or the turning force, what is the direction of turning? Yeah, or in which direction does the body turn or rotate? Yeah, so it depends upon the point of application of force and direction in which the force is applied. For example, if this is the body and the force is applied here, what will happen? The body will rotate in an anti-clockwise direction. Yes, similarly, if there is another body and the force is applied at this point, what will happen? This force will turn the body in a clockwise direction. Now, how do I quantify torque? What is a positive torque and what is a negative torque? It depends upon what is the direction of turning. Yeah, so depending upon the direction of turning, we can quantify or classify torque as positive and negative. So the torque is positive if it tends to rotate the body anti-clockwise. So the anti-clockwise torque is positive. Torque is negative if it tends to rotate the body clockwise. Clockwise torques or moment is negative. Yeah. Coming to unit, CGS unit of torque is dyne centimeter. Since torque is force times distance between the line of action and the axis of rotation, force has the unit Newton or dyne in CGS, and length, distance has meter or centimeter in CGS. So the CGS unit of torque is dyne centimeter and SI unit is Newton meter. In terms of gravity, it is kgf meter. Kgf is also a unit of force, yes, and gf centimeter. So kgf meter in SI unit and gf centimeter in CGS unit. How are they all related? We know that 1 Newton is 10 to the power 5 dyne. So 1 Newton meter is 10 to the power 7 dyne centimeter. 1 kgf meter is 9.8 Newton meter. And 1 gf centimeter is therefore 980 dyne centimeter. Since 1 Newton meter is 10 to the power 7 dyne centimeter. Moving on. Why is quantifying turning very useful? First, they have lots and lots of applications in daily lives. Yeah. First is opening a door. Should you place the handle close to the hinge or away from the hinge? Yeah, placing the handle close to the hinge would make our life extremely difficult. Yeah, that's why the handle is placed away from the hinge, so that the distance D between the line of action and the axis of rotation is maximum. Yes, the steering is turned by applying a torque. How? One hand is here and it applies a force in upward direction. The other hand is here and it applies a force in downward direction. Both this force rotate or turn the steering wheel. Other example is a seesaw. There is a guy standing here having a weight W1 and there is a girl standing here having a weight W2. The guy is trying to turn the seesaw anti-clockwise and the girl is trying to turn it in a clockwise direction. Yes, and that is the whole game of seesaw. Moving ahead, some more applications. The first, we always use a spanner with a long handle. Why? Because we know that torque is force times displacement. Yes, so to produce the largest torque that we can increase either our force, which is effort, which demands a lot of effort. Second is by increasing the distance between the axis of rotation and the handle, the point of application of the force. Yes, so that's why spanners have long handle. Why? To produce the greatest torque available. Yeah, to maximize the magnitude of torque produced. What is the other example? Using gears in cycle. Yes, you must have noticed it is easier to pedal the cycle when the gear toothed we use the bigger gears. Yes, and when we use the smaller ones, it is a bit more, it demands a little more effort. Why? Because the distance from the axis of rotation to the point of application of force, which is through the chain, increasing. Yeah. So when the gear is big, the distance is more, and when the gear is small, the distance is less. So the torque produced in this case will be greater than the other one. One more important topic is equilibrium. What is the meaning of equilibrium? Equilibrium is when a number of forces acting on a body produce no change, that is called equilibrium. What? When the number of forces acting on a body produce no change, that is the state of equilibrium. Yeah, equilibrium can be of two types. First, a static equilibrium. Static equilibrium means when the body remains in a state of rest under the influence of applied forces, that is static equilibrium. And dynamic equilibrium is when the body remains in a state of uniform motion under the influence of applied forces. Yes, so there are two kinds of equilibrium. First, a static, which is when a body remains in a state of rest under application of applied forces. Yes. Second is dynamic. Dynamic is when a body keeps on moving in a uniform speed or in a state of uniform motion even under the influence of applied forces. That is a state of dynamic equilibrium. Yeah. There are certain conditions for equilibrium, which is the algebraic sum of all the forces acting on the body should be 0. So the algebraic sum of all the forces acting on the body should be 0. Second, the algebraic sum of all the moments acting on the body should be 0. Sum of all torque should be 0. What it means, we are going to explore next. Yes. So the examples of static and dynamic equilibrium. The first example is a book lying on a table. Yeah. So the forces are first the weight of the book itself. Second, the normal reaction from the table. The table, because of its contact, is producing a normal reaction. Yeah. So there are two forces acting, normal and the weight. Yeah. And under the influence of these two forces, the state of rest remains. That's why the book is said to be in a state of static equilibrium. Yeah, the normal balances the weight of the book. Second, when we see the weighing balance, the beam balance, what happens when the weight on both the pans are equal? Then the moment generated because of this weight, which is in clockwise direction, is equal to the moment generated by this weight, which is in anti-clockwise direction. Yes, since both the moments are equal, no change happens. This is also an example of static equilibrium. Next, let's see an example of dynamic equilibrium. The first is the motion of electron around the nucleus. What happens? The electron is continuously moving in a uniform speed around the proton. Yeah, there is a continuous electrostatic attraction. Yeah, continuous electrostatic force is being applied on the electron, pulling it towards the proton, yet the electron keeps on moving in a circular path in a constant speed, in a uniform circular motion. This is an example of dynamic equilibrium. One more example of dynamic equilibrium is rain falling. Yeah, so what happens when it's raining? The raindrops initially they gather speed, and at a particular point in their fall, they acquire something called terminal speed. And after that point, they keep falling downwards with that same speed, with a continuous and uniform speed. Yes, so a raindrop after a certain distance starts falling in a constant speed called the terminal speed. Yeah, then the forces acting on it are the weight of the drop, the air resistance, the drag forces. Yeah, they balance each other out and the drop falls with a uniform speed. This is an example of dynamic equilibrium. This brings us to a very important concept called the principle of moments. What is the principle of moments? Something very, very simple. It is, if a body is in equilibrium under the action of a number of coplanar forces. What is the meaning of coplanar? In a single plane. Yes, the algebraic sum of moments of the forces about any point is 0. Sum of forces, the sum of moments of the forces about any point is 0. Yes, like we saw in the weighing scale. There is a force acting here and here, but they produced equal and opposite anti-clockwise and clockwise moments, which cancelled each other out. Yeah, so sum of clockwise moments equals sum of anti-clockwise moments. Yeah, anti-clockwise are positive and clockwise is negative, so their addition cancels each other out and we attain 0 as the algebraic sum. Yeah, a beam balance works on the principle of moments. Let's verify it. How do we verify it? Let's take a ruler. Yeah, and in its midpoint, let's support it in the midpoint so that it is free to move in this direction. It can either rotate in anti-clockwise or clockwise direction. Yeah, and let's take two masses. Yeah, we will take two masses and hang it at different distances. Yeah, so let us say that this distance is d1 and this mass is m1. What we will do now is we will take another mass m2. And we will try to hang it on the ruler at a point such that the ruler stays horizontal. Yeah, if there is only this mass m1 on the ruler will tend to fall or rotate in anti-clockwise direction. Yes, and if there is only mass m2, what will happen? The ruler will try or would want to rotate or turn in a clockwise direction. Yes, so we want to place m1 and m2 at such distances d1 and d2 such that the ruler remains horizontal. What does it mean that ruler is in equilibrium? Yes, how do I verify it? By verifying it while doing the experiment, we will find out that the moments are equal and opposite. Yeah, so the moment, let's calculate it. The moment due to m2, it is force times the distance. Yes, so what is the force? Force is the weight of m2. The weight is m2 into g, mass times gravity. Yeah, so the moment is m2g into the distance d2, and it is negative because it is producing a clockwise turning motion, so minus. Answer is minus m2 d2g. Similarly, the moment due to m1 is the weight of m1, which is m1g times d1, and it is positive since it is causing an anti-clockwise turn. Yeah, and since the ruler remains horizontal or is in equilibrium, what happens? The sum of anti-clockwise moments and sum of clockwise moments are the same. So what happens? m1g times d1 plus negative m2g d2 is 0, or m1 g1 d1 is m2 g2 d2, which is the sum of anti-clockwise moments equal to the sum of clockwise moments. Yeah, let's verify it for more number of masses. Yeah, so let's say this is the midpoint. The ruler is free to move about this axis. Yeah, let's take two masses this time. This is mass m1, this is mass m3, m2 and m4. All the masses are different. d3, d1, d2 and d4 are chosen in such a way as to keep the ruler in a horizontal position. Yes, so the ruler is horizontal, which means ruler is in equilibrium. Yeah, so let's write the moment of a force about the midpoint. What is it? Let's write the clockwise moment first. The clockwise moments are what? Due to m2 and m4, m2g d2 plus m2g d4. And the sum of anti-clockwise moments are m1g d1 and m3g d3. And since they are in equilibrium, sum of all moments should be 0. Yeah, clockwise moments, the sign is negative. Yeah, sum of all moments are 0. So m1g d1 plus m3g d3 minus m2g d2 m2g d4 m4g d4 equal to 0. Yeah, taking these to the other side, we get m1g d1 plus m3g d3 is m2g d2 plus m4g d4, which is basically sum of clockwise moments is equal to the sum of anti-clockwise moments. Yeah, so the principle of moments is what? It states sum of anti-clockwise moments equals sum of clockwise moments. Yeah, principle of moments is just this. Sum of clockwise moments is sum of anti-clockwise moments. Moving on. Parallel forces and couple. Yeah, an arrangement of two equal and opposite parallel forces acting along parallel lines at different points is called a couple. What do I mean by that? Yeah. So we have a force is applied here. Yeah, it should be equal and opposite. So if I apply a force F here, F force should be applied here in opposite direction. Acting along parallel lines, they should be parallel to each other at different points is called a couple. Yeah, so let's say the distance between them is D. A couple can be balanced by an equal and opposite couple only. F force here tries to turn the object in anti-clockwise direction, and the force F in the left end also tries to move or turn the body in an anti-clockwise direction. So what is the moment of a force? Let's take the midpoint O and let's try to calculate the turning effect produced by a couple. Yeah, so midpoint, so the length is d by 2. So because of this force, the turning effect is F times d by 2 anti-clockwise, which is positive, and the turning effect due to this force is force times d by 2 anti-clockwise, so it is positive as well. So total torque is F d by 2 plus F d by 2 is force times the distance between them. Yes, so the moment of a couple is the product of one of the forces F times the distance between the two forces, which is D. What is the unit? Same as that of torque. What are the examples of it? Example is a steering. Yeah, so a force is applied upwards, F rotating the steering in an anti-clockwise direction, and then equal and opposite force is applied in the left side, diametrically opposite, downwards, producing an anti-clockwise turning effect. Yeah, so the couple in this case would produce a torque of F into D, force into the distance between the two forces. Yeah, or when you pedal a cycle, the cyclist uses two of their legs, two of their feet. No? So the force is equal and opposite on the pedals. Or the turning of a tap, we use two fingers, equal and opposite forces, producing a couple. Moving on, let's talk about center of gravity. Yeah? Center of gravity is, I think, a term which I think it's used by the sports analysts and numerous other people in our daily lives. Yes, so let's understand what it really means. Yeah, let's say there is an object. So the objects are made up of very, very small particles. Yeah, small particles. Let's say these are the particles, yeah, and so on. Everywhere we have these particles. Yeah, and each of these particles has a weight. Let's say the weight is small mg. Yeah, all these weights, all these arrows are small mg. And the particles make up the object. So the weight of the object would be the sum of all these small weights. Let's say the weight is W. Yeah, capital Mg. Yeah, so what did we do? We assume there is an object. The object is made up of small particles. The particles weight is mg. Yeah, and the particles make up the object. So the object's weight, which is capital Mg, is the summation of all these small mg's. Yeah, so the point where I assume the resultant or the entire weight of the object to act through is called the center of gravity. What does it mean? If I place the object on top of my finger at this point on the center of gravity, the object will not fall. Yes, so it can also be defined as a point in the body, point of the object wherein if placed there are no resultant gravitational torque. Yeah, so it's a delicate thing to understand. It's a point about which if the object is kept there is no resultant gravitational torque. Yeah, if you're able to understand it, good. Not able to understand it, no issues. Yeah, let's understand it deeper. What is it? It's a point of application of resultant force on the body due to Earth's attraction. Yeah, the Earth is attracting everyone, everything in this world, right? So the resultant weight of the body acts on the center of gravity. Okay, let's move on. In the coming slides, you will be able to understand what I am trying to say. The resultant force is called the weight of the body. This you guys already know. You know this already. Position of center of gravity depends on its shape. What does it depend on? It depends upon the shape of the body. Yeah. For a symmetrical shaped uniform object, G means the center of gravity is its geometrical center. Yeah. So you must have seen all those tricksters, yeah, having the football balanced on their fingertips, basketballs balanced on their fingertips. How do they do it? They do it by keeping the center of gravity directly on top of the finger. Yeah, if the center of gravity were here, the weight would act here and produce a torque, a gravitational torque, and make the ball fall down. Yeah, if the center of gravity were here, what would happen? The same thing. The weight would act here and produce a gravitational torque, and the ball would topple down in this direction. Yes, moving on, let's get a bit more accustomed to the concept of center of gravity. Center of gravity for a uniform, regularly shaped symmetrical object is at its geometric center. Yeah. For example, for a sphere, it would be at its center. The center of the sphere, for the sphere, either hollow or solid. For hollow or solid, for sphere, it is the center. Yes, for a cube or a cuboid, it would be the intersection of its diagonals or its center. Yeah, for its cube, it's the center. For cuboid, it is intersection of diagonals. Yes, for a cube, cuboid, and sphere is done. Let's see what is it for a triangle. Yeah, for the triangle, it is the intersection of its medians or the centroid. Yeah, the centroid is the point. Suppose you make a line from every vertex, yeah, joining the midpoints to the edges, to the opposite edges. That is the centroid. For triangle, for any triangle, it is the centroid is the center of gravity. Yes, for a parallelogram or rectangle, for a parallelogram or rectangle or square is what? It's the intersection of diagonals. Wherever the diagonals intersect, that is the center of gravity. It is the intersection of diagonals. For a cylinder, it is the midpoint of its axis. Yeah, the midpoint of its axis is the center of gravity. A solid cone. For a solid cone, it is at a point h/4 from the base. This is the base. Yeah, it is along the axis and at a height of h/4. H is the height of the cone. Yeah, the center of gravity lies at a location h by 4 from the base of the cone. Yeah, for a hollow cone, it is at a distance of h by 3 from the base of the cone. Is the base, h is the height, it lies at a distance of h by 3. Yeah, so it's important from ICSE perspective to know about some of these locations. Yeah, you should check out the page in your textbooks where it is given in detail in a tabular and very neat format about the location of center of gravity for regularly shaped objects. Yeah, for again, for a circle it is the center, for a rod it is the midpoint. Yes, it's very commonsensical. Yeah, suppose this is a pencil. Where would you keep your finger? On what point of your finger or the pencil would you want to place your finger in order to balance it? How would you balance that pen? By placing it approximately in the center, right? Yeah, so that point is called the center of gravity. Yes. Okay, moving on. Why do we need to understand about center of gravity? Why is it so important? Because the stability depends upon it. Yeah, just like we saw, right? If the football, yeah, if the finger is placed directly under the center of gravity, you may balance it. Yeah, and you can do all those tricks. But if this finger is kept either left or the right of center of gravity, a torque will be generated and the football will topple. Yeah, so this concept can be used to make objects around us more stable. Yeah, as I said, physics is a study of why things happen. So if you want to know that what makes one thing more stable than the other, you should know the concept of center of gravity. Yeah, so stability depends upon, number one, position of center of gravity, and number two, area of its base. Yeah, for example, if we have a cone, yeah, cone placed on a floor in this direction is stable than compared to a cone placed upside down. Why? Area of the base. See, area of base, right? Even if I disturb the cone, yeah, push it slightly left and right, it wouldn't topple. But in this case, even if I somehow balance it, little force will cause it to tumble down. Yes, so area of the base also guarantees stability or determines stability. Yeah, for a stable body, center of gravity should be as low as possible. Hence, the lower part of the body is made heavy. Like in boxing, when you want to box, yeah, you're continuously moving upper body, but you are told to bend and box. Why? Because you want to make your center of gravity as low as possible. Yes, if you are a power lifter, what happens? You want to make your thighs strong. Yeah, and you want to keep your back straight and you want to bend down. Why? To keep your center of gravity as low as possible. Yeah, in cars, why don't you make a car that looks like this? Yeah, because you want to make the center of gravity as low as possible. That's why the car is shaped like this. To make the center of gravity as low as possible. Yes, I hope this comes out to be clear. So for a stable body, center of gravity should be as low as possible. As low as possible. Number two, the base area should be large. The base area should be large. Yeah. What happens if this base area is large? If the object is toppled, like in the case of this cone, yeah, it is tilted. The center of gravity is lying here. So the line joining the center of gravity to the center of earth is still passing the base. So it's going to come back to its original position. It's going to have the tendency to come back to its original position. Yeah, but in this case, what happens if it is gently tilted? Gently tilted, the center of gravity is here, and the line joining the center of gravity to the center of the earth is not passing from the base. Hence, it will topple down. The example of an inverted cone and a straight cone is a good example. Yeah? You may use this in an ICSE exam. So if a body is slightly tilted, the center of gravity rises higher and it has a tendency to regain its original position. Yeah, that's why when we lift something heavy, we tend to bend. We tend to bend. Why? To improve our balance. Yeah, when we are surfing, if you have seen people surfing, what happens? They try to bend their knees to bring their center of gravity as low as possible to get balance. Yeah. So there are two factors for stability. Number one, position of center of gravity and area of its base. Moving on. Uniform circular motion. Yeah. When a body moves on a circular path at a constant speed, its motion is said to be uniform circular motion. Yes, the name itself suggests it. Yeah. Uniform means constant speed. Circular means circular. Motion means something is moving, right? So when a body moves on a circular path at a constant speed, its motion is called uniform circular motion. Yeah, the magnitude of acceleration remains constant because speed is not changing, but the direction keeps on changing. What are the examples? Examples are the earth going around the sun. Yeah, it is going around the sun in a circle. Or the moon going around the earth. The moon goes around the earth, revolves around the earth. Yeah, so that's a circular motion. Or you tie a stone, tie a string to a stone, and you keep on winding it, rotating it in a circle in a constant speed. That comes to be a uniform circular motion. The other example is of an hydrogen atom. What happens? An electron is revolving around the nucleus, which is a proton, at a constant speed. So it's a uniform circular motion. Yeah. So in uniform circular motion, there are certain things happening. We want to understand how uniform circular motion happens. How does it happen? Yeah. So at every instant of uniform circular motion, the direction is changing. Direction of the body is changing. So there must be some force causing that change. Yeah, there must be some force causing that change, and that force is centripetal force. Yeah, centripetal force is a force acting towards the center on a circular path. What? Centripetal force is a force acting towards the center on a circular path. Yeah, so according to Newton's first law, moving body travels along a circular path with constant speed if and only if there is a force acting on it towards the center to change its direction continuously. Yeah, and that force is centripetal force. And the value of that force is F equals mv squared upon r. Yes, so for the hydrogen atom, the centripetal force is provided by electrostatic attraction. Yeah, the proton attracts the electron and provides the necessary force for uniform circular motion. In the case of the earth going around the sun, the gravitational force provides that force of centripetal. Yeah. In the case of the stone tied to a string and wound up, tension in the string provides that force of centripetal, provides the centripetal force. Yes, it's a very natural consequence of Newton's first law. If a change is happening, a force must be causing it. That force here is centripetal force. And as per Newton's third law, every force or every action has an equal and opposite reaction. right? So a centripetal force must be having something which is equal to it but opposite. Yes, and that force is nothing but the centrifugal force. Yeah, the example of this force is, yeah, when you sit on a merry-go-round, or in park, if you have seen a structure like this in which you rotate it, sitting on it you will feel as if you are being pushed away from the center. Yes, that force is called centrifugal force. One thing to note is that centrifugal force is not a real force. Centrifugal force is a pseudo force. That is, it does not exist. It exists only when you are sitting on the ride, on the jhula. Yeah, sitting outside, standing outside, centripetal force wouldn't be needed to explain your actions, explain what is happening to you. But when you sit on the ride, you feel a push, you feel something pushing you out from the center, away from the ride. That force is centrifugal force. So a force acting on the body away from the center of circular path is called centrifugal force. According to Newton's third law, an equal and opposite reaction force always exists. Centrifugal is that to centripetal force. Yeah? So difference between centripetal and centrifugal force. It's a common, very important question as compared, in the context of ICSE. So what are the differences? Yeah, centripetal is what? A force acting on the body towards the center. Centripetal is a force that acts on the body towards the center. Yeah, but centrifugal force is a force that acts on a body away from the center. Yes, centripetal force is a real force. It exists. Centrifugal force is not a real force. It's a pseudo force or a fictitious force. Yes, examples of centripetal force are, just give the examples, is electrostatic interaction when there is a proton and there is an electron. The electrostatic force of attraction gives you the centripetal force. Centrifugal force examples are when you sit on a merry-go-round and you feel that pushing you away from the center, that is a centrifugal force. Yes, that is the end of this chapter. The entire chapter is done. The theory related to force, yeah, the first chapter of ICSE physics is done. Yeah, thank you, and I really hope this lecture was understood by all. If not, please feel free to ask your questions in the comment section, or if you are my student, personally in my WhatsApp number that I shared with you, or physically in the class when we meet. Yes, thank you, and see you in the next one. There will be one more video on this chapter containing questions and its solutions. Yeah, the questions would be very, very important in the context of ICSE 2026, and I really wish to provide even more questions, including the concepts that we studied in chapter 1, yeah, to refine your concepts, yeah, to refine everything that you have learned. Yes, okay, see you in the next one. Thank you.